Quasars, scientifically called quasi-stellar radio sources, are intensely luminous, distant, extremely fierce celestial objects that were discovered by the intense radio emissions radiolog quasars gave off. They are old galaxies that generate huge amounts of energy. Quasars are some of the most energetic and bright objects known, giving off indescribable and incomprehensible amounts of power. They can emit hundreds, even 1,000 times more energy than that of the entire Milky Way galaxy. This is due to their active galactic nuclei. Active galactic nuclei are due to a supermassive black hole in the center of a galaxy, creating an accretion disk of matter which can produce relativistic jets. These are a pair of jets of large yet condensed outflows of energy that flow out opposite of each other, adjacent to the accretion disk. These jets and accretion disks generate a very high amount of energy across the entire electromagnetic spectrum. This includes everything from X-ray emissions to radio and infrared radiation. They have a very high redshift, meaning that they are ancient and very distant from us. Using Hubble's law and their redshifts, quasars are calculated to be between 600 million and 28.85 billion light-years away. There's still a lot we don't know about quasars, but the Sloan Digital Sky Survey has been collecting and pulling an immense amount of data that's open to the public. I used the 10th SDSS data release for my dataset. I analyzed the correlation between quasars' radio flux and their magnitudes and colors by creating a code that would generate these following graphs. On the y-axis is the radio emissions, and on the x are the PSF magnitudes. The left plot's y-axis is graphed using a linear scale, while the right plot's is graphed using a logarithmic scale, because magnitude is really a logarithmic measure of flux. The blue and rightmost points are all the U-grid's magnitude values by themselves. U for ultraviolet, G for green, R for red, I for near infrared, and Z for infrared. Color is represented by subtracting the magnitudes. Take the U, or ultraviolet, magnitude, and subtract the G, or green magnitude from it. The resulting number will tell you how much of each magnitude is present. The higher the value, the more of the subtracting magnitude it is. The lower, the more of the value of being subtracted from. This is because magnitudes decrease with increases in intensity or brightness. Magnitudes are taken by taking pictures through 5 U-grid's filters. The filter blocks out all light except the color you want. If you look, the average magnitude for the standalone U-grid's values is around 20, marked by the yellow dotted line. For the subtracted magnitudes, the average is actually 0.5, but has been marked as 0 by the orange dotted line. By both plots, but especially the logarithmic one, you can see that quasars are highly redshifted by the subtracted magnitudes. The bigger the Y value means the more the color is towards the longer wavelengths of the spectrum. This is proven true in these graphs. The y-axis is still radio emissions, but now the x-axis is the redshift of the quasars, 0 marked by the dotted green line. Notice how there's no points before 0, meaning all the measured quasars had redshifts greater than 0 and also less than 6. The following are more graphs, broken down so you can see each component. The top row is the logarithmic y scale, the second row is the linear scale, with the x-axis scale to the data points, and the last row is the linear scale with the x-axis being the same for all of them. The yellow dotted line marks 20. From left to right, it is the magnitude values of U, G, R, I, and Z. These next graphs are the subtracted magnitudes. From left to right, it is the logarithmic plot, then the scale to the data plot, then the plot that is scaled to match the rest of the plots. This was done so I could overlay them to display them all on one graph later. Notice how far to the right the points go from 0 when subtracting green from ultraviolet. The spectrum goes from short wavelengths to long wavelengths, ultraviolet being shorter than green. As an object moves away from an observer, they get redshifted, and their wavelengths appear longer. There are exceptions, such as the ones going left of the orange bar. This would mean that they have very short wavelengths, and despite being redshifted, they are still very ultraviolet in color. This trend continues through the graphs, and as it goes for the longest wavelength part of the spectrum, it becomes more balanced. Also, throughout the graphs, there is a common trend of, while high magnitude doesn't determine if we'll have a high or low radio emissions, as magnitude increases, thus apparent brightness and intensity decreases, the amount of radio emissions it can give off also decreases. This is my code. My code is quite repetitive and utilized matplot and numpy. I extracted data from the dr10 fits file, then plotted it using matplot's scatter function. I also utilized this built-in log function for the logarithmic graphs. To set maxes and mins for the y, I set it to be the maximum radial flux value and then 0 to be the minimum. I used numpy to subtract the magnitudes from each other, and Python's built-in color system to assign colors. The code set my data to be plotted it, saved it using savefig, then went to the next plot to place that data, until it reached the bottom, where it quickly generated averages and maxes and mins for redshift, radial flux, and all the Uyghur's values in the subtracted counterparts.